Hello everyone, my name is Jonathan Gagnon. I work as a researcher at Folks VFX. I'm going to present a new approach to do texture synthesis on a fluid simulation. This work is the result of a collaboration between the ETS in Montreal, Carleton University in Ottawa, and Folks VFX. I've been asked several times to add details on a fluid simulation. In most cases, we have a surface mesh outputted from a fluid simulator, for example, Houdini. We want to synthesize a texture based on texture exemplars. However, it is impossible to do this with the current DCCs out of the box. Therefore, we need to develop something. Fortunately for me, I'm not the first one that was trying to do such thing. Quatra was able to synthesize a texture on a fluid animation using an optimization method to find the best match for each pixel on the surface. It works well, especially with structured patterns, such as the green one. However, it is limited to low-resolution texture exemplars. Moreover, as you can see on the right, it produces a washout effect with stochastic and isotropic textures. The washout artifact can also be visible even for structured textures, as we can see in the yellow region in the middle. To have a closer fit to the velocity field, you propose to use deformable patches of texture that are advected with the flow. It works very well, but it is limited to 2D fluids. To avoid popping artifacts, when they are removing or adding new patches, they use a temporal fading. However, since the fade rate is fixed, it is sometimes too slow to remove some stretchings and blurred artifacts. It is possible to use rigid patches to texture a fluid, as the approach of Gagnon et al. 2016. Where they use subset of texture samples advected on the surface of the fluid. The main issue with this approach is that we can see the patches if they are large, especially when patches are rotating. Visible patches can be fixed by using deformable patches, as with the approach of Yu et al. 2011. And Gagnon et al. 2019. However, they have two main limitations. When the fluid stops, the fading continues. And when we take a closer look, we can see ghosting artifacts. Therefore, what we propose is to use patch erosion to overcome ghosting. The erosion removes patches based on local deformation to overcome the fading when the fluid stops. And finally, the use of deformable patches to prevent the rigidity and distracting rotation of patches. This is the overview of the proposed approach. Our approach is designed to add texture details to the surface of the fluid. It is applied as a post-process and does not interfere with the fluid simulation. The approach takes two inputs. First, we take as input an animated mesh and a velocity field. The animated mesh of the fluid is typically a completely different mesh at every frame. The velocity field has no restriction other than allowing sampling at arbitrary location on the fluid surface. We also take a texture example and a related feature map. In this example, we use a displacement map as our feature map. On the first frame of the fluid animation, we scatter patch meshes over the surface. To have a well-distributed patches, we use a Poisson disk distribution. Patch meshes are extracted from the fluid surface mesh. From the position we want to add a patch on the fluid surface, we select connected polygons in its vinicity. We then flatten the mesh to define UV coordinates with which we can associate a texture sample. When we have our set of patches, we can compute the feature-aware patch erosion. The patch erosion is done with the help of the feature map. The goal is to be able to erode a patch according to the feature of the texture sample. Here's a side view of the feature map, where we have values that go from 0 to 1. We want to do the patch erosion from the outside towards the middle. Therefore, we define a function that will create a round shape combined with the features of the texture. Here, we have a side view of the resulting erosion map. Now let's have a look at a single patch erosion. In this example, we are decreasing the quality of the patch every frame uniformly. As you can see, the erosion acts at the texel level. When the whole surface has been covered with patches and eroded, we can visualize the result by giving a single color per patch. This is the result of the eroded patches on a 3D fluid. With the eroded patches computed, we can synthesize the output texture. For each texel of the output texture, we have one corresponding eroded patch texel. We then use these texels colors to create the output texture. So from the eroded patches, we obtain the output texture. This was for the first frame of the animation. We will now explain how we deal with the remaining frames. For the subsequent frames, we do an advection of the patch meshes. What we want to advect are the polygon's vertices. This is an example of a patch being advected on a fluid surface. After each frame, we project each patch vertex onto the surface to make sure the patches remain on the surface. We detect topological changes by computing the distance between each advected vertex to the surface. If the distance is above a threshold, we remove the vertex and the connected polygons. When the advection is done, we can compute the vertex quality. Basically, we want to know if some part of the patch is excessively deformed, and then make it disappear by erosion. Therefore, the vertex quality will tell us which texel from the patch we should keep. To compute the vertex quality, we use the distortion metric proposed in the approach of Sorkin et al., where it compares the initial triangles with the deformed triangles. This gives us a value between 0 and 1 for each vertex. With the vertex quality computed, we can do the patch erosion. The erosion is done by removing regions of the patch where the deformation exceeds a threshold. Here is an example of how it looks on a single advected patch. And here is how it looks with several patches. We left some space between patches in order to see the shape of the patches. As you can see, when patches are deformed and eroded, it creates big gaps in the texture. This is why, after the erosion of advected patches, we flag the texture gap in order to add new patches. Indeed, whenever we find a texel with no associated patch, we add a full-sized patch centered on the missing texel. The patch is added beneath existing ones. This way, we avoid having popping artifact in the animation. Finally, we can compute the resulting output texture. Here is the result of this example. We validated our approach using several texture samples. Here, for example, we have the same fluid simulation textured with 3 different samples. We also validated our approach with 3D viscous fluids, such as this one. It also works with structured patterns, such as this example. We also test with other 3D fluid simulation scenarios. Note how the synthesized texture adapts well to the overall movement, as well as the filaments and sheets of liquid. Here is the same fluid simulation with another texture sample. This is a lava simulation with no texture. We control the color with a simulation of the lava temperature. Here is the result, texture by our approach. Thanks to the texture synthesis, we can have much more details on the fluid surface. We compared our work with previous approaches, especially the dynamic lap texture of Gagnon et al. 2016 and the deformable patches approach of Gagnon et al. 2019. In these comparisons, we use the same fluid simulation and a similar patch size. On the left, we can see the rotation of patches for the dynamic lap texture method. What we can see is that the result of the dynamic lap texture approach is faithful to the exemplar. But we can easily see the boundaries of the patches. It is even worse when using large patches. Since it uses rigid patches, the result feels rigid as well. And the rotation of the patches are distracting. When looking at the deformable patches method, we can notice that it is less faithful to the exemplar because of the blending. Also, when the fluid stops, the blending continues. Finally, in comparison, our approach is faithful to the exemplar. It has no blending, and it does not feel rigid. However, it is possible to see the patch boundaries during the erosion. Here is another comparison with a completely different texture exemplar. With the deformable lap texture representation, the texture conforms well to the movement of the fluid surface. We compared the fluid's velocity field, shown in blue, with the optical flow of the rendering, shown in green. The two fields are in close agreement, demonstrating that the texture synthesis is able to match the liquid flow. In this paper, we presented a new patch-based approach for synthesizing textures on fluid surfaces. Our approach extends lap textures to fluids. We use a feature-aware patch erosion approach in order to better preserve similarity to the exemplar. Using erosion rather than fading eliminates ghosting artifacts. Further, unlike methods depending on temporal fading, our texture stops changing when the underlying fluid stops moving. There are still some opportunities for future work. We would like to investigate more deeply the patch replacement strategy, ensuring that we get good surface coverage without excessive number of patches. Future work could explore automatic methods for computing a feature map from an exemplar. Finally, texturing surfaces with dynamic and non-homogeneous textures is an area of interest. Thank you for watching.